It's from section 5.5, and it's about number sets. It's really just about, for starters, being able to identify what numbers belong to what set. You can see the natural numbers are all positive numbers, whole numbers, all positive, but including zero, right? Natural doesn't include zero. Integers are negative and positive numbers with no fractions or decimals. A rational number is anything you can write as a fraction. And irrational is something that you can't write as a fraction, basically. And then real numbers includes all rational and irrational numbers. So the first one just wants me to classify the numbers. So all the numbers that are natural numbers, remember those are all positive numbers, excluding zero, no fractions or decimals. So this one actually qualifies square root of 81 because that is 9. So square root of 81 actually qualifies as natural. Whole numbers, remember now you're including zero, so now we'll include 0, and we have 9. Integers, remember, are positive or negative numbers, no fractions, no decimals, so -7 works. 0 is an integer. 9, again, is an integer. Moving right along, rational numbers. And anything I can write as a fraction is rational. So the first three, -7 over 1 is a fraction. I can write it as a fraction. 0 over 0, 9 over 1 is 9. So those are all rational. You see the pattern here. A lot of these number sets include the previous ones. Not perfectly that, but anyhow. Next, well, -3/4 is already a fraction, so that's obviously something I can write as a fraction. 0.6 can be written as, remember we did go over how to write these, but at the end of the day it's going to be 2/3. 0.6. 7.3 is something we could write as a fraction. The irrational numbers are the ones we could not be able to write as a fraction. Like the square root of 5, most square roots that aren't perfect squares are going to be irrational. Pi is a decimal that goes on forever, which is aka something I wouldn't be able to write as a fraction. Real numbers are basically all these numbers. All the numbers are real numbers, rational or irrational, so all of the numbers are real. I suppose, versus imaginary numbers. Oh, dang it, you guys couldn't even see that. So I'm just going to show you that now. Either way. Next one, I'm just going to go through these answers again. Remember, all the natural numbers are all the positive numbers, excluding 0, no fractions, no decimals. So the square root of 9 is 3, so that actually does qualify. My whole numbers are now including 0, so 0 is there, include 3. Whole numbers, they're all positive numbers, including 0, no fractions, no decimals. Next I have my integers. These are also no fractions, no decimals, but they can be positive or negative, so -9 will add to this mix. 0 and 3 are also part of it. Moving right along, rational numbers. Any number I can write as a ratio or a fraction. Oh shoot, guys. Sorry about that. I messed up on what you can see, but like you heard what I said. I was just listing the numbers out, and you can see the answers here. So, rational numbers, anything I can write as a fraction. I could write -9, 0, or 3 as a fraction, so those all count. Now, -1.3, I can also write that as a fraction. This 0.3 is actually supposed to have a line above the 3, not on the side. 10 is not a perfect square. That's going to be an irrational number. And then pi, since pi is irrational, pi divided by 2 will stay irrational. So from that list, pi over 2 and the square root of 10 are the irrational numbers. As you can see here, commutative, associative, and distributive. If these were regular numbers, you would know like 3 times 7 is the same as 7 times 3, right? 3 times 7 is 21, 7 times 3 is 21. Basically, you can multiply in any order. If you're just multiplying a group of numbers, 2 or more, the order in which you multiply won't matter. So you can look here and see what's what. If you're adding or multiplying, you can change the order. That's commutative property. Same thing here. If you're just adding or just multiplying and there's parentheses, you can move the parentheses almost wherever you want and it won't change the final answer. So if you're moving parentheses, that's associative, and then distributive is the most obvious one, not obvious, but the most familiar one, where we know if we multiply a number a number that's outside parentheses into the parentheses, we can get a new value, and we're distributing it, right? That's distributive property. So anyhow, right here, all they do is change the order in which they multiply. So that's gonna, if you look up there, that's gonna be commutative property, where all you do is change the order in which you either multiplied or added. On this one, 4 plus 7 plus 6, 4 plus 7 plus 6. Notice the order of the numbers didn't change, but the parentheses moved over. That is going to be associative property, again stating that I guess you could think of it as the parentheses will associate certain numbers, but if all you're doing is adding, it doesn't matter which numbers are in the parentheses, you're just adding, the answer will stay the same. Here we can see that 2 is outside of parentheses and it's 3 plus radical 5, and 2 times 3 is 6, 2 times radical 5 is 2 radical 5. All that happened really here is distributing, so of course distributive property is the property that's taking place. This one right here, square root of 2 plus square root of 3 plus square root of 7, and then square root of 2 plus, notice they actually changed the order of the radicals here. The parentheses didn't move. The parentheses stayed in the same place, but the order of the radical 3 and the radical 7 changed, so that is commutative. Again, the parentheses didn't move, just the two values, so that's definitely commutative. It wasn't the parentheses that moved. So anyhow, I'm going to go through these next 4 here. Let's see, 4 times 7 times 3. The only thing that moved is the parentheses, so that's going to be associative if the parentheses move. On this one, let's see, they didn't even distribute. They just changed the order of the radical 5 plus 4, 4 plus radical 5. That won't change the final answer, but it is showing the commutative property of addition. If you change the order in which you add, nothing changes in the final answer. Here, let's see, it looks like they distributed, right? 3 times radical 5, 3 times 4 is 12, so this is showing distributive property. And then this one, let's take a look. 2 times square root of 3 plus square root of 7, and then they say radical 3 plus radical 7 times 2. Looks like to me they just moved around the things they were multiplying. They moved the 2, and the 2 is getting multiplied by the parentheses, right? Whatever's in there. So, so 2 times whatever's in the parentheses, and then whatever's in the parentheses times 2. So again, they just moved around things they were multiplying already. So that is commutative. That one's a little tricky, but if you think about it, it makes a little more sense that they moved what they were multiplying. They didn't actually move the parentheses. Either way, it is commutative. Hopefully you can move along with that. And then this next idea here, let me get this on screen better. This next idea is, honestly, it's easier to explain if I just do a problem. So it's talking about integers, right? Are they closed when you multiply? Basically, what that is saying is if you multiply any 2 integers, will the answer always be an integer, right? So 2 times 2 is 4. Remember, integers are just positive or negative numbers, no fractions, no decimals. So, so again, I'm trying to basically show you that I'm multiplying integers, 2 positive numbers, a negative number times a positive number, negative 3 times 4 is negative 12, multiply 2 negative numbers, negative 5 times negative 6, that's going to give me a positive 30. So when you guys do these problems, what you're trying to do is use what it said, right, integers and multiplication, and you're trying to see if you can get an answer. Right? When you use integers and you multiply, you're trying to see if you can get an answer that is not an integer. Okay? If I can multiply 2 integers and get an answer that is not an integer, then I would say, oh, the integers are not closed with respect to multiplication, meaning I could multiply 2 integers and get an answer that is not an integer. But as you can see here, I think they are closed. I think the integers are closed when you multiply, because multiplying 2 integers, I got an integer for an answer. Multiplying 2 integers here, my answer was an integer. and then I multiplied 2 more integers just to check, and again my answer was an integer. So the answer is, in this case, when you multiply 2 integers, your answer is always an integer. And that, another way to say that is to just restate that question. Yes, integers are closed. Sorry, it's a little sloppy. But integers are closed. Integers, the answer is always an integer. So integers are closed with respect to multiplication. No matter what 2 integers you multiply, the answer is always going to be an integer. So when you say they're closed, excuse me, when you say they're closed, basically what you're saying is, you'll never get an answer that is not an integer when you multiply 2 integers. So hopefully that makes sense, but we'll keep trying. Are irrational numbers closed with respect to multiplication? Well, remember, irrational numbers are numbers like the square roots of numbers that are not perfect squares, like the square root of 2, right? So if you multiply the square root of 2 times the square root of 5, those are 2 irrational numbers. You get the square root of 10, that's another irrational number, but right? By the way, all you need is one example to prove that they're not closed, but definitely use a few examples before you decide that they aren't closed, right? So here's what I'm trying to do, right? I'm trying to multiply 2 irrational numbers and check to see if I can get just a rational number, basically, if I can get a number that is not irrational when I multiply 2 rational numbers. So I'm multiplying 2 irrational numbers here, square root of 2 times square root of 2, which is square root of 4, which is 2. This is rational. This one example proves that the irrational numbers are definitely not closed with respect to multiplication. I'm just going to put not closed. Hopefully you will be good to connect it to irrational numbers are not closed with respect to multiplication. Again, check it out. If you multiply 2 irrational numbers, it's possible to get an answer that is rational. So they're not closed with respect to multiplication, irrational numbers. Are natural numbers closed with respect to division? Well, we could check on that. Remember, natural numbers are, if you look back, it's just 1, 2, 3, 4, 5, 6, 7, 8. It's just positive numbers, no fractions, no decimals. So you could try it. You could be like, well, 6 divided by 3 is 2. So natural number, answer's a natural number. You can, remember, you're looking just for one example to show that they're not closed. 10 divided by 5 is 2, but all you have to do is this, right? All you have to do is flip either one of those. If you go 5 divided by 10 and you get 0.5 or a half, you no longer have a natural number. So these are not closed. Natural numbers are definitely not closed. When you divide, you can definitely divide 2 natural numbers and get an answer that is not a natural number. So again, try to process what it's saying, right? If you take 2 natural numbers, and divide them, right? Take 2 natural numbers and divide them. Will the answer always be natural? Well, nope. There's my example. So let's just say not closed, and of course, it's saying that natural numbers are not closed when you divide. So use at least 3 examples to show these. If you're going to say they are closed, definitely check at least 3 times. So are natural numbers closed with respect to multiplication? Remember, natural numbers are just positive numbers. 2 times 4 is 8, also natural. 3 times 20 is 60, that's natural. 5 times 11 is 55. So 3 examples is good enough. Every time I multiply 2 natural numbers, I get a natural number for the answers. So this one is a yes, they're closed. And then, are the integers closed with respect to division? Remember, integers are positive or negative numbers, no fractions, no decimals. So, you can go like 10 divided by negative 2, your answer is an integer. 5 divided by, I don't know, I'm going to go with 5 divided by 3. 5 divided by 3 is like, it's like 1.6 forever. So so there it is. 1 example is all I need to show that they're not closed.